Now we continue the introduction to the course with a discussion of the general issue of the data deluge and various ways of looking at that. First, we start off with the really most direct way of specifying it. This is this well-known chart from IDC, which plots the total amount of data created and shared as a function of time, with the estimate of essentially 8 zettabytes in 2015. Note that 1 zettabyte is about 10 to the power 10 of what you might have on a local storage of a reasonable size personal machine, 100 gigabytes. More precisely, a zettabyte is 1,000 exabytes, and an exabyte is 1,000 petabytes, and a petabyte is 1,000 terabytes. So zettabytes is quite a large number, and it just keeps going on. It's also worth noticing that a terabyte costs around $50 today in your local store. So this, if you look at the total cost, is 10 to the ninth. I mean, a zettabyte is 10 to the ninth times terabyte, so that's $50 times 10 to the ninth storage cost. It's practical, but quite large. If we now look in more detail at some sizes of sources of data, web pages, tens of petabytes. And there are 40 times 10 to the ninth of those. YouTube has, we have an actual graph on YouTube. It's in May of 2013, there's 100 hours of video uploaded per minute. So you're not going to watch that. It's impossible. Not all of it. And 100 hours per minute uploaded 6 months ago, 8 months ago. Quite impressive. And that's up from 20 hours a minute 6 years before then. So that's many petabytes per year. And a Large Hadron Collider, which we'll discuss, is 15 petabytes per year. Radiology, excluding cardiology, that means so you have MRI and things like that in it, is 69 petabytes per year. It's sort of the largest amount of technical data. There's some pretty big systems coming along. The Square Kilometer Array Telescope, which is maybe, I don't know, 10 years out. That's 100 terabits per second. Having obviously dramatic computing and data analysis challenges. If you look at the whole field of Earth observation, that's a few petabytes per year. On the other hand, if you look at a subset of that, earthquake science, there is maybe totals of, actually broadly construed, it might be 100 terabytes. But if we look in detail, what's most relevant is just a few terabytes, because that field doesn't have quite the right type of satellite enabling to get a lot of data. If you go to what we do, the work we do, which were mentioned in the last section of this class, the work we do on remote sensing in Antarctica and Arctic, that gathers hundreds of terabytes per year, maybe up to a petabyte in a year or so. Finally, if you do simulations produce output. That output is terabytes per second from when the machine will get around 6 years from now, which is an exascale machine. A machine capable of doing exaflops of computation every second. Here's this YouTube picture we just showed as to document the previous slide. If we now go to look on the web and other people's talks and just sort of get some idea as to why big data is interesting, here I have a set of slides from Tom Davenport, who was an evangelist in this area. So we have companies like LinkedIn using social media analytics and they were always sending me messages about who I ought to talk to and things like that. We even analyze this course on LinkedIn, so it's sort of analyzing that data as well. We have call centers which are doing voice analytics. That's been revolutionized by deep learning technology, which is giving you much better voice recognition capability. Text analytics, that's obviously pretty important. Looking at tweets or analyzing data from customers or in a more automatic, precise fashion. Video analytics, that's how you spot that's obviously of great importance in defense applications where video feeds are generating many petabytes of data per hour. So that's intelligence, policing, monitoring, and the retail and in retail stores, not just security, but just actually recording what people do, so you can know how to stock those shelves in a more efficient fashion. And then finally, we have genomic data, and we know personalized medicine is going to be revolutionized by the fact that everybody will have their genome in their electronic medical record. So here we have IBM. This is from these all come from the same fall to 2012 conference on big data at Berkeley. Pretty interesting conference with a lot of good talks. And here's IBM's view of big data with various aspects. We have up around here, we have Google, Facebook, etc., pouring data in. We have the decision makers getting information and business analysts helping them. We have the finance part of the company analyzing all the financial data, call data, and due to finding where billing is not working properly. Marketing obviously is mining data to find out what works. That's one of the biggest uses on the internet, where you try to do custom ads and custom placement, custom generation of web pages to maximize the amount of money to the people sponsoring those pages. So here we have business developments and how we partner with other companies into sort of complex, multifaceted optimizations. So that's another important aspect of this field, that the analytics can link analytics across its life cycle, and like it can link web pages through several clicks to find some optimal solution. Meanwhile, all of this has to actually not only have UPS deliver our packages on time, something which was a sensitive problem this Christmas, but we need to actually have the internet giving us good performance. So here's Tom Davenport again. So what is this data? I mean, that's actually a non-trivial question. There isn't actually not a lot of agreement on what big data is, and as opposed to say little data or medium data or giant data. Big data is actually almost today all data, because what really counts about big data is not the size, but the way it's used, the fact that the data itself is leading to conclusions. But if you want to be technical, it's big, so petabytes in size, unstructured, diverse, and it does not easily get analyzed by traditional online transaction processing, SQL databases, and so on. And then it comes from all these areas: internet, genomics, voice and video, sensors, or more generally, the world of the Internet of Things, with its 75 billion devices by 2020. And then we need to gather it all together, fuse it, classify it. Lots of these technology algorithms are classification algorithms. And then you need to count how much of it there is of each type. And then you just need to draw conclusions. That's converting data to information, to knowledge, to wisdom, to decisions, to whatever you're trying to do. So we need to not only have batch data, but we need streaming data. There's been a whole new exciting developments of new types of computer science algorithms with streaming data as opposed to ab initio analysis of batch data. Now these companies like Netflix and Amazon and Google have so much data in place, they don't really want to rerun a batch operation. They just want to say, I just got another 10 petabytes of data. I'll update my database of 1,000 petabytes with this 10 petabytes and get some conclusion. And us more humble souls with smaller data sets need to do the same thing in a somewhat more modest fashion. So we now need, and then all of this requires a range of skills which are a different combination from those that maybe many people were trained in the past. And this course is part of a spectrum of courses offered by the School of Informatics and Computing to actually train data scientists. And these are scientists, not just analysts. They involve analytics and expertise in analytics, but they involve people who understand the whole process of a data life cycle. And they are able to, if necessary, take the very latest additions of the, say, the Apache Big Data Stack and add it on for a nifty new analysis system. So this data keeps on coming on. Maybe look at those plots as a function of time. It's coming up by zettabytes per year. So I ain't gonna wait for you. You better get on board. So we need to, we're not just making SQL queries, which is the traditional maybe way that data was thought of. We're filtering it. We're applying nifty classification algorithms. We're structuring it, and we're using MapReduce, and we're using Hadoop, and we're using HDFS and Storm and things like that. We are building content analytics tools, natural language processing. We need to manage the fact that the data is not always unique. And we're putting the analytics in the cloud. We're learning about machine learning because that's of growing importance, because that in some sense is what the analytics programs are. They are machine learning programs. And everything, I mean, Apache has taught us with its great success in Hadoop and things like that, that open source, including here it mentions the important statistics package R, which is open source, is a very important concept which is being, which underlies the revolution we see. It's remarkable to me how much proprietary work is done on the open source Apache big data software systems. And finally, we have here the rather nifty picture from The Economist. It's rather old now, 2010, which is just trying to give a rather spectacular view of the data deluge. And of course, it only has a single zettabyte of data because it's 2010, but it's still pretty big. And it's nice to think of all those bits pouring down from the rain. We just had a pretty difficult time with lots of snow pouring down, but bits are coming down at increasing volumes. And whether or not climate change is giving us more or less snow or rain, I can assure you the trends that mankind has instigated, they're going to give us more and more data, whatever we do. So we better get on board and learn how to process it. Thank you.